All right, Chemistry 111. This is practice exam 5. It covers chapters 9 and 10 in our textbook. Okay, let's see here. Choose the best answer. Multiple choice. Question number 1. The number of lone electron pairs in the N2 molecule, so that's the dinitrogen molecule, and you should be able to draw the Lewis structure of N2. So if we have two nitrogens, nitrogen has 5 valence electrons. It's in group 5A times 2 of those. That means we have a total of 10 valence electrons. And when we connect those together, we end up with a triple bond between the two nitrogens and a lone pair on each of the nitrogens. So that means we have a total of 2 lone pairs. Question number 2, which one of the following compounds uses both ionic and covalent bonding? Well, if we look at B, B is just a model or a molecule of carbon dioxide, which only has covalent bonds between the carbons and the oxygens. If I look at carbonate, you might be fooled into thinking, well, it's got a 2 negative charge, that's ionic. Well, no, it is just an ion. Carbonate is an ion, right? If I draw the Lewis structure of carbonate, I have 2 oxygens that both have a negative charge, but there's no ionic bond here because there's no cation next to the carbonate. The next one is magnesium chloride, MgCl2. This is just an ionic compound because it's made of a metal and a non-metal. The next one, C6H12O6, that's glucose. So glucose is only made from covalent bonds. There are no ionic bonds in a molecule like glucose, right? And there's no metals in there either, so there's no way to have an ionic bond. However, if I look at aluminum sulfate, I have the sulfate polyatomic ion. I have 3 of those, SO4 2 minuses, right? And those are all ions. And then I also have 2 Al3 plus ions, right? The Al3 pluses, those are metals. The sulfates, those are nonmetals. They're anions. And so I have the ionic bond between the positively charged cation, the negatively charged anion. And I also have covalent bonds in a sulfate polyatomic ion, right? Because inside the sulfate, I have 2 double bonds to oxygen like this, and I have 2 single bonds to oxygen, and there's 3 lone pairs on each of those and 2 negative charges. And so the answer is the aluminum sulfate. Question 3. The covalent bond with the greatest polarity would form in which of the pairs below? So if we compare the difference in electronegativity between all of these elements in these bonds, I mean, we can immediately cross off D, right? Because there's no difference in electronegativity between bromine and bromine. Now, if we just draw part of the periodic table here, I'll just scribble it down. We have boron, carbon, nitrogen, oxygen, fluorine. Then we have silicon, phosphorus, sulfur, and chlorine, bromine, and iodine. That's just a little bit of the periodic table. And we know that electronegativity increases going up and to the right. So electronegativity increases going across the period from left to right, and it increases going from bottom to top of a group. And so if we compare the difference in electronegativity between the boron and the oxygen, well, we can do some very quick and dirty math here. In that, as I told you when we looked at electronegativity, as long as you can remember that carbon has an electronegativity of 2.5, nitrogen is increased by 0.5, sorry, oxygen increases by 0.5, and then you get over to the mighty fluorine, which is 4.0. So that makes boron 2.0. If we look at the difference between the carbon and the oxygen, that's going to have a difference in electronegativity of 3.5 minus 2.5, which is 1. If you look at the boron and the oxygen, that's going to have a difference of 1.5. Now, what about sulfur? Okay, sulfur and oxygen. Well, hopefully you remember the 1 down and over 2 rule. If you go 1 down and over 2, you end up with an atom that has close to the same electronegativity, which means that the sulfur is going to be around 2.5 and the phosphorus is going to be around 2.0. So the sulfur oxygen has a difference in electronegativity of about 1, and the carbon phosphorus has a difference in electronegativity of about 0.5. That means the greatest difference in electronegativity is the boron and the oxygen. Question number 4 says classify the carbon-chlorine bond in CCl4 as ionic, polar covalent, or non-polar covalent. Well, let's go back over here. And when we go down from fluorine to a chlorine, remember the down 1 and over 2 rule. That means that the chlorine is going to have an electronegativity of about 3.0. So that means we've got our carbon, which is 2.5, and our chlorine, which is 3.0. The difference in electronegativity is going to be 3 minus 2.5, which equals 0.5. What was the cutoff? When we had a difference in electronegativity that was greater than 2, we considered that to be ionic. Nonpolar covalent bonds were those that had electronegativities that were less than 0.5. But then if I had a difference in electronegativity that fell in the range of 0.5 to 2.0, then that is considered polar covalent. So since polar covalent starts at 0.5, that means that this bond is polar covalent. The Lewis dot symbol for a calcium ion is, well, if you look at calcium, it is in group 2A. Just a plain old calcium is going to have 2 dots. We could write them like this. I could write them like this, right? We want to have the maximum number of unpaired electrons. But we know that calcium loses 2 electrons to become isoelectronic with a noble gas, right? Calcium will lose 2 electrons to become isoelectronic with argon, which is a noble gas that has 18 valence electrons. So we end up with the calcium 2 plus ion plus 2 electrons. So that means that the Lewis dot symbol for the calcium ion is nothing more than calcium 2 plus. Question number 6, which of the elements listed below would most likely form a polar covalent bond when bonded to oxygen? Hopefully you can see right away that we can eliminate oxygen, can't we? Because if we have an oxygen-oxygen bond, there's not going to be a dipole in there. So we can eliminate the polar covalent bond there. The problem with sodium, magnesium, and aluminum is that these are all metals, right? So how are these going to interact? Can we have sodium oxide? Sure, we can have sodium oxide. Can we have magnesium oxide? Sure, we can have magnesium oxide. Can we have aluminum oxide? Sure, Al2O3 is aluminum oxide. All of these 3 oxides, these are all ionic, right? Because these are the bonds between a metal and a non-metal. However, the bond between an oxygen and a hydrogen, that's a polar covalent bond, right? With a dipole that goes in this direction. Just like the oxygen-hydrogen bonds that we see in a water molecule, which are polar covalent. So the answer is the hydrogen. Question number 7 says the number of lone electron pairs on the perchlorate ion is. Well, let's start by drawing out the perchlorate ion. We've got ClO4 minus. Chlorine has a total of 7 valence electrons. Oxygen has a total of 6 valence electrons times 4 of those. Oops, and I have a -1 charge. So that gives me 24 plus 8, which gives me a total of 32 valence electrons. Now, I'm going to start with my chlorine as my central atom like this, and I'm going to start drawing bonds to my oxygen atoms like this. Now keep in mind that chlorine is in the 3rd period, so it can expand its octet. If we expand the octet of the chlorine so that it has no charge, and we fill up the octets of all of the oxygens that surround it, like this, we have a negative charge on this oxygen. We have no charge on any of the other oxygens. And just to double check the formal charge here, chlorine has 7 valence electrons, subtract 7 sticks and 0 dots means it has a charge of 0, so that looks good. Now we tally up the total number of lone electron pairs in this molecule. we have what? Let me zoom in on it here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 electron pairs. So those are my lone electron pairs. 9. Number 8. Which of the following is a useful guideline for the application of formal charges in neutral molecules? If we have a neutral molecule, like let's say we have, I don't know, something simple. Let's say we have water, right? Water is a neutral molecule. Nitrogen, we saw that earlier. That's a neutral molecule. If you have carbon dioxide, that's a neutral molecule. That's a Lewis structure, right? A neutral molecule is going to have a Lewis structure that's preferred where you have no formal charges. No formal charges are preferred. B says the preferred Lewis structure is one in which the positive formal charges are on the most electronegative elements or atoms. That makes no sense whatsoever. Okay, the most electronegative atoms are the ones that are going to preferentially take the negative charges, if there are any. Lewis structures with large formal charges are preferred. That is definitely incorrect. So the answer to 8 is A. Which one of these would have the highest melting point? Well, you remember Coulomb's law, which states that the force of attraction between the cation and the anion is the product of the charges of the cation and the anion divided by the distance between the two nuclei. And so the shortest distance is going to cause the greatest force of attraction between the cation and the anion, and the highest charges are going to form or going to result in a higher force of attraction between the ions. So if we compare all of these, all of them are potassium salts: potassium iodide, chloride, fluoride, and bromide. That means that this part is constant, right? They're all +1 times -1. Okay, fine. Well, now all we have to do is examine the distance between the nuclei. So if the potassium doesn't change, which one of these? Oh, sorry, it says the lowest melting point. I was thinking with the highest melting point. So basically we're looking for whichever one has the weakest, we'll say weakest forces of attraction between the cation and the anion. I'm like, that's not right. Anyhow, so we're looking for whichever one has the weakest attraction. And so we are looking for not the shortest, but we're looking for the largest. Sorry, my mistake. I didn't read the question properly. We're looking for the biggest radius. And we know that when we go from fluorine to chlorine to bromine to iodine, the iodine is the largest, right? Size increases as we go down a group as the principal quantum number increases. So since the potassium and then the iodine are the farthest apart, that means that this number is going to be the biggest, which is going to cause this to be lower. The forces of attraction is lowest, and that's going to result in the lowest melting point. It's going to be easier to break the potassium and the iodine ions apart and cause them to melt. All right. Question number 10. Carbonic acid is a weak acid, contributes to the taste, and produces the carbon dioxide bubbles in all carbonated beverages. How many valence electrons are used to show the Lewis structure of carbonic acid? Now, this is a question where I would expect everybody to get it right. It's not a complicated question. It's something that we've done many times. Hydrogen has 1 valence electron. There are 2 hydrogen atoms. Carbon has 4 valence electrons. There is 1 carbon. Oxygen has 6 valence electrons. There are 3 of those. So we have 2 plus 4 plus 18. That gives us 18 plus 6, which gives us a total of 24 valence electrons. And there you have it. And the reason I put this on here is just in case, somebody was like, well, I'll just, tally these up. No, those are the lone pairs. Those are unpaired electrons, but those do come from valence electrons. Also, the electrons in the bonds come from valence electrons. All right, number 11. Assuming the octet rule is obeyed, how many covalent bonds will an oxygen atom form to give a formal charge of 0? Well, I could give you any number of examples. Let's say you have something like methanol. So methanol is wood alcohol. It can get you intoxicated, but it can also cause you to go blind. You see that there's an oxygen there that has 2 bonds and 2 lone pairs. What if you look at a water molecule, right? Water, the oxygen in water has 2 bonds and 2 lone pairs. What about carbon dioxide? Both of these oxygens have 2 bonds and 2 lone pairs. And so oxygen always has 2 bonds and 2 lone pairs when it has a formal charge of 0. Question 12. List all types of bonding present in calcium carbonate. What does calcium carbonate look like? We've got the calcium 2+ ion, and we've got the carbonate 2- polyatomic ion. Well, there's nothing else I can say about the calcium, but we can see that we have an ionic bond, right, between the metal and the polyatomic ion, which is made from nonmetals. Well, let's examine the structure of the polyatomic ion. Carbonate looks like this. We have a double bond to our oxygen and 2 single bonds to these oxygens over here. So we have negative charge here like this. Now, there's also polar covalent bonds, right? Because there's a dipole going this way and this way and this way, right? We know the difference in electronegativity between carbon and oxygen is 3.5 minus 2.5, which is 1.0. So that's a polar covalent bond. And so the answer is 1 and 2. Ionic bonds and polar covalent bonds. There are no nonpolar covalent bonds in calcium carbonate. Question 13. Which one of these polar covalent bonds would have the greatest percent ionic character? So basically we're looking for the most or the greatest, let's see here, the largest difference in electronegativity. Okay, you can see that you have hydrogen in each one of these. And you know that when you go from fluorine to chlorine to bromine to iodine, that electronegativity decreases. So electronegativity increases going up the group. So the greatest difference in electronegativity will be that between the hydrogen and the fluorine atom, right? Hydrogen is about 2.1 and fluorine is about 4.0. So the delta En is going to be equal to 1.9 approximately. That's a strongly polar covalent bond. You think about ionic bonds, it's right on the cusp. 2.0 is considered ionic. All right. The beryllium tetrafluoride, or the fluoroberylate ion, is BeF4 2-. Either name is fine. The formal charge on the beryllium atom in this ion is, now, this is one where you kind of have to invoke your knowledge of drawing Lewis structures, right? We know that in the beryllium, or from the beryllium in BeF4, we've got 2 valence electrons plus 7 for each fluorine. There's 4 of those, plus 2 extra electrons. So that gives us 4 plus 28. That gives us a total of 32 valence electrons. Well, even if you didn't tally up the total number of valence electrons, and I guess you kind of have to solve the problem, you know that fluorine only ever forms 1 bond and has 3 lone pairs. No exceptions. There are no exceptions to that rule, and this isn't an exception either. So look, now here I have 8. 8 times 4 gives me 32. 8, 16, 24, 32. So all of the electrons are used up. Now when we calculate the formal charge of the beryllium, we have 2 valence electrons, subtract 4 sticks and 0 dots, which gives us -2. And so that is the charge on the beryllium. Here is a 2- charge. Question 15. Shown here is the Lewis structure of the chlorate ion that obeys the octet rule, showing all non-zero formal charges. How many resonance structures for the chlorate ion are there that obey the octet rule? Well, I'm going to start by redrawing the chlorate ion. So I have my oxygen over here, my chlorine. There we go, like this. And remember, a resonance structure, okay, this is not a perfect representation of the chlorate ion, is it? Right? We know that the double bond doesn't reside just between this chlorine and this oxygen. We know that each one of the bonds here has some partial double bond character, right? Some of the time it can be on this vertical carbon-oxygen bond, the way I have it drawn. So if we just take this molecule, or this, oops, am I missing? I'm missing a negative charge here, aren't I? There we go. If we take this polyatomic ion, we copy it. So we'll take it and we'll just, come on. Copy and paste it over here. There we go. We'll draw a resonance arrow like that. And now what we're going to do is we're just going to remove that pi bond, move this negative charge, we'll move this, and then we'll put the double bond here, and we'll put the lone pair over here and have the negative charge over here. But we also know that the double bond could reside between these two atoms over here. So let's give it a shot. We'll paste the molecule again, or the polyatomic ion, I should say. There we go. We do the same kind of thing here where we'll delete that bond, delete this negative charge, delete that lone pair, and then we'll put the double bond over here, put this lone pair back here, and there you go. Those are the three possible resonance structures for the chlorate ion. So we have a total of 3 resonance structures for the chlorate ion that all obey the octet rule. Are there other structures you could draw that don't obey the octet rule? Sure. That's not what we're asked to do. Question 16. Which one of the following is most likely to be an ionic compound? Well, ionic compounds are formed between a bond between a metal and a non-metal. If you look at ammonia, nitrogen and hydrogen are both nonmetals. Sulfur and oxygen are both nonmetals. Chlorine and fluorine are both nonmetals. Phosphorus and fluorine are both nonmetals. But iron is a metal. It's a transition metal. And chlorine is a non-metal. And there you have it. Question number 17. How many covalent bonds will be drawn to the phosphorus in PO43-, the phosphate ion, for the dot structure that expands the octet to minimize formal charge, and if necessary, places negative formal charges on the most electronegative atoms? So it's nothing more than drawing the Lewis structure of the phosphate ion. We have PO43-. So from our phosphorus, we have 5 valence electrons plus 6 times 4 plus 3. That gives us what? 24 plus 8, which gives us a total of 32 valence electrons. Start with putting our phosphorus in the middle. We'll draw some bonds to oxygen like this. Now it's telling us that we're going to put the negative charges on the most electronegative atoms. Oxygen is much more electronegative than phosphorus. And so how do we have a negative charge on an oxygen? It's when the oxygen has a single bond and 3 lone pairs. So if we draw this, then we have a negative charge here, negative charge here, negative charge here, and we need a 3-. How many electrons have we used so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. If we've used 26, that means you got 6 electrons left over. Where are they going to go? 1, 2, 3, 4, 5, 6, like that for the phosphate. So it's asking us how many covalent bonds are formed. Well, we have a covalent bond here, another one here, another one here, and we have 2 covalent bonds here. So that gives me a total of 5 covalent bonds. Which of the following Lewis structures is incorrect? Could anybody help me out with this one? Does anybody see one that's a glaring error? You guys have all seen enough Lewis structures by now that you should recognize when you see one that's funky. There's one here that's really off the wall. Yeah, thanks, you guys. It's C. Absolutely. So, in the interest of time, it's 6:37. Something I wanted to do with you, and that is to look at some of the questions that deal with using the molecular orbital diagrams for valence electrons. So looking at molecular orbital diagrams. And that's why I posted the handout for exam 5 in the chat earlier on this evening. So you can get that out, and it shows you the molecular orbital diagrams for dilithium to nitrogen and then from oxygen to dineon. So we're going to use those to solve a problem like question 30. So I'm going to skip ahead, and that's because we're running out of time. It says, consider the species Cl2 plus, Cl2, and Cl2 minus, and determine which of these species is going to be paramagnetic. If it's paramagnetic, that means it's going to have unpaired electrons. And so in order for us to determine whether these ions in the chlorine are going to have unpaired electrons, we have to look at the molecular orbital diagrams. So how many valence electrons do we have in Cl2? We have 7 for each chlorine times 2, which gives me 14. So that tells me that in my Cl2 plus, my Cl2, and my Cl2 minus, right? If in Cl2 I've got 14, if I have minus, I add 1, I've got 15. And in Cl2 plus rather, I've got 13 valence electrons. So this is the number of valence electrons, okay? 13, 14, and 15 respectively. Now, if you look at the handout that I posted in the chat earlier this evening, you'll see valence electron molecular orbital diagram for lithium to nitrogen, and then valence electron molecular orbital diagram for oxygen to neon. Well, what comes in between oxygen and neon? The answer is fluorine. And so since chlorine comes right below fluorine, we can use that molecular orbital diagram in order to solve this problem. Now, again, we're just using the valence electrons. So I'm going to write down the molecular orbitals in the order that they are on that diagram. Again, I'm just going to write down the orbitals that are in the middle to make it as simple as possible. So I start with a sigma. I'm going to have a sigma 3s orbital, followed by an antibonding sigma star 3s orbital. Then I'm going to have my pi 3y orbital, my pi 3z orbital. Then I've got my pi star 3y orbital and my pi star 3z orbital. Am I missing one here? Oh, I skipped my sigma 3p. Let me just move this up a little bit here. It's not a big deal. There we go. I'll squeeze it in here. I've got my, I'll just write it like this, my sigma 3p, like that. And then I've got my sigma star 3p up on top. So this is my sigma star 3p. Now, hopefully you took the time to watch my lecture videos that I posted wherein I cover all of this information. So when we have a star, that's an antibonding molecular orbital. And when I don't have a star, like this one here, this is a bonding MO. Okay, so again, the star means an antibonding molecular orbital. So for our Cl2, let's just start filling it up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so all of the electrons are paired up. We have no unpaired electrons. And so Cl2, I'll write it over here, Cl2 is actually diamagnetic. All of the electrons are paired up. Now, what about the chlorine plus ion? It's got 13 valence electrons, so I'll just remove one of the electrons here. Now I end up with an unpaired electron. And so the Cl2 plus ion is going to be paramagnetic. What about the Cl2 minus? Well, that means I need 2 more electrons compared to my Cl plus, so 1, 2. Now I have an unpaired electron here in the sigma star 3p orbital, and so that is going to be paramagnetic as well. It's also going to be attracted to a magnet. And so the answer is the dichlorine with a positive charge, or the dichlorine cation, and the dichlorine anion. Let's take a look at questions 41 and 42, which also deal with the same concept using those molecular orbital diagrams. Question 41 says, what is the bond order in F2 minus? Well, how many valence electrons do we have? We've got 7 for each fluorine times 2 plus 1 for the negative charge. That gives me 15 valence electrons. Again, if you look at the molecular orbital diagrams that I have on that handout, you'll see, again, there's one that goes from oxygen to Ne2. and fluorine is in the middle there. So we can just copy it straight off of that slide or that handout, if you will. So let's write it down, and this time I'll try not to skip any orbitals. We get our sigma 2s, followed by our sigma star 2s. Then we have our sigma 2px. We've got our pi 2py, our pi 2pz. We've got our pi star 2py. We've got our pi star 2pz. Then we've got our sigma star 2px, like that. And again, I just copied that straight off of the sheet, okay? Now, it's kind of hard to see. It's not, maybe, but I need a new prescription anyway. But yeah, you can see it in there. You can see that next to the pi's, it doesn't have the principal quantum number, but I like to include it anyway. It doesn't matter. You're going to get the right answer if you fill it in correctly. So we've got 15 valence electrons. Pitter patter, let's get at her. Look, we got 1, 2, 3, 4, 5, 6, 7, 8. Following Hund's rule, 9, 10, 11, 12, 13, 14, 15. So we end up with an unpaired electron. This ends up being paramagnetic. All right, what's bond order? Okay, again, if you watched my videos, you'd see that bond order is equal to 1/2 times the number of electrons in bonding orbitals, subtract the number of electrons in anti-bonding orbitals. So let's give it a shot. 1/2 times the number of electrons in bonding orbitals. Who's in a bonding orbital? Let's see. Anything that doesn't have a star is a bonding orbital. There you have it. We've got a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonding orbitals. In anti-bonding orbitals, we'll highlight those in green. 1, 2, 3, 4, 5, 6, 7. So we've got 7 electrons in anti-bonding orbitals. 8 minus 7 is 1 times 1/2 gives you a bond order of 1/2 or 0.5. There you go. So that is the bond order in the F2 minus ion. Let's try one more that involves using those molecular orbital diagrams. Again, you can see we're using the molecular orbital diagram for O2 to Ne2, no, not N2, to Ne2, since the question is about O2. It says, consider these species, O2 plus, O2 minus, and O2. Which one is going to be paramagnetic? Right? What does paramagnetic mean? Which one is going to have unpaired electrons? Well, let's take a look here. If we have O2 plus, if we have O2, and if we have O2 minus, how many total valence electrons does O2 have? All right, we've got 6 valence electrons times 2, that gives me 12. So here I'm going to have 13, and here I'm going to have 11. Let's write down the orbital diagram. Could I copy this one? I suppose I could if I erased everything. So I'll just copy this one because it's the exact same one. Just to save a little bit of time, copy it, and I'll paste it. Of course, you would write these out on your scratch paper, or there we go. Let me just move down a little more. Here we go, like this. Now I'm just going to clear it all off so we can just recycle it. So give me a second. So let's start with O2, which has 12 valence electrons. Again, we follow the Aufbau principle, and we follow the Aufbau principle and Hund's rule. So let's start with O2. 12 valence electrons. 1, 2, 3, 4, 5, 6. Hund's rule. 7, 8, 9, 10, 11, 12. We've got 2 unpaired electrons. Therefore, this is paramagnetic. What if we add an extra electron to have 13 for O2 minus? We'd put it here. That's also going to be paramagnetic. Okay, now I'm going to remove all of them just to show you one more time. And we're going to figure out O2 plus, which has 11 valence electrons. Watch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's got an unpaired electron. So that tells me that all 3 of these are paramagnetic. All 3 are paramagnetic. And that goes right back to the beginning of the section on molecular orbital diagrams. Why do we have to do this? If you're wondering, what's the whole point of this, Mr. Dion? Well, the way the book starts out the section on molecular orbital diagrams is this. He says, if you take oxygen, and if I asked you to draw the Lewis structure of oxygen, you would draw O2 like this, wouldn't you? Okay? You draw 2 oxygens with 2 bonds, 1 sigma, 1 pi, and then a total of 1, 2, 3, 4, 5, 6, 7, 8 unpaired electrons, 4 lone pairs. But if you take liquid oxygen and you put it between the poles of a very strong magnet, what you find is that the oxygen actually gets held. It gets held by the magnet. So that shows you that there's a limitation to this Lewis structure, doesn't it? Because there's no unpaired electrons in this Lewis structure. None. However, if we look at the molecular orbital diagram of O2, right, which is this, we end up with 2 unpaired electrons. Right? And that shows us that we have to sometimes use more than one model to explain the behavior of a molecule. Right? There's nothing wrong with the Lewis structure that I have drawn here in the yellow circle. However, it doesn't explain why the molecule is paramagnetic. And this is why sometimes we have to use molecular orbital theory. Again, the solutions to the rest of the problems. So I'm just going to back up. I left off somewhere around where? I left off at question 18. So the rest of the answers for questions 19 through the end are found in the videos that I have posted in the D2L announcements. So you have those, and I also posted the solutions in the chat this evening, so you have those at your disposal as well.